All right, let's talk about one of the most fundamental pieces of all electronics, the amplifier. It's that little bit of magic inside almost everything that takes a tiny, weak signal and makes it powerful, useful, and hopefully crystal clear. So let's start with a really basic question. Imagine you've got this tiny electrical signal, maybe from a microphone, maybe from a guitar pickup. How in the world do you boost it so it's strong enough to drive a massive speaker, but without turning it into a garbled, distorted mess? That, right there, is the entire game.
So what are we even aiming for here? What does a perfect amplifier actually do? Let's take a look at the ideal scenario.
And here it is. This is what we're shooting for. You see that small wave going in? The amplifier's job is to create a much, much bigger version of it coming out. But, and this is the key part, it has to be an exact copy. The shape is identical, just scaled up. We call this linear operation, and it's basically the holy grail for anyone who cares about clean, high-fidelity sound.
But, we don't live in a perfect world, and if you don't set up your amplifier just right, things can go sideways fast.
Yikes. Just look at this. That beautiful, smooth wave from before, it's been totally flattened on the top and bottom. This is called clipping, and it's a nasty form of distortion. It's that awful, crackly sound you hear when a speaker is pushed way too hard. Essentially, the amplifier is hitting its physical limits. We call them saturation and cutoff, and it just can't reproduce the signal faithfully anymore. The result? A mangled mess.
So how do we stop this from happening? How do we avoid this disaster? Well, the secret is all about finding the perfect sweet spot for the amplifier to work in. And to do that, we have to get familiar with a little something called the quiescent point, or the Q point.
So what on earth is a Q point? Think of it like this. It's the transistor's idle setting. Before you feed any signal into it, the transistor is just sitting there waiting. The Q point defines that exact waiting state, its baseline voltage and current. And believe me, getting this idle setting right is absolutely everything.
Okay, this graph might look a little intimidating at first, but the idea behind it is actually pretty simple. That straight diagonal line, that's the DC load line. It basically represents every possible idle state the transistor could be in. Our Q point, that little dot right in the middle, has to live somewhere on that line. Then, when our music signal comes in, it makes the operating point swing up and down around that Q point. And that's why its location is so incredibly critical. If we put the Q point right in the center of that line, our signal has the maximum possible room to swing up and down without hitting the rails, without hitting saturation or cutoff. It has plenty of what we call headroom.
But just look what happens if we get it wrong. Here on the left, the Q point is set way too high, too close to saturation. And bam, the top of our wave gets chopped right off. On the right, it's too low, near cutoff, and the bottom gets clipped. Remember that ugly distortion from before? Well, now you know exactly what causes it, a badly placed Q point.
Okay, so our mission is clear. We need to park that Q point right in the middle, and this is crucial, we need to make sure it stays there, even if the temperature changes or other things fluctuate. This kicks off our quest for stability, and we're going to look at 3 different ways to build this circuit. Our first contender is the most basic approach you can possibly imagine. It's called bass bias. I mean, it doesn't get much simpler than this, right? You've got your power supply and just one single resistor, RB, that feeds the idle current into the transistor space. It's super easy to design and build, so what's the catch? And here's the verdict. The pro? It's simple. The con? Well, it's a deal breaker. This circuit is wildly unstable. The Q point completely depends on a transistor property called beta, which is kind of like its personal amplification factor. The problem is, beta can change like crazy with temperature, and it can be different even between 2 transistors from the same batch. So that perfect sweet spot you calculated, it's just going to wander all over the place. Not good. Okay, so clearly we need a smarter design. Our second attempt brings in a really clever trick called negative feedback, which lets the circuit basically regulate itself. Now, these 2 circuits are a much cleverer approach. The one on the left, emitter bias, adds a resistor at the bottom. The one on the right, collector feedback, connects the base resistor back to the output. What both of these do is create a kind of self-correcting loop. If the current tries to creep up for any reason, the circuit automatically pushes back, keeping that Q point much, much more stable. So, the verdict? This is a huge step in the right direction.
These feedback-based circuits are way more reliable than that simple base bias design. The Q point is much less likely to drift. But can we do even better? Oh yeah, we absolutely can.
And that brings us to the main event. It's time to meet the undisputed champion of biasing circuits, the voltage divider bias. Take a good look at this circuit right here. This is probably the most common, most robust biasing method you're going to find out in the real world. And there is a very, very good reason for that. It solves our stability problem in the most elegant way possible. So, what's its secret sauce? Why is this one the winner? Well, instead of relying on the unpredictable transistor, it uses those two resistors, R1 and R2, to create a rock-solid, predictable voltage at the transistor's base. And by doing that, it makes the Q point almost totally independent of that flaky beta value we talked about. This design locks the sweet spot in place, and it does not move. So let's just put it all on the table. This chart really tells the whole story, doesn't it? Base bias is simple, but its stability is poor. Feedback bias is a good improvement, using that self-correcting trick. But voltage divider bias? It gives you excellent, rock-solid stability that doesn't care about beta. It is the clear winner for any serious amplifier design. So, after going through all of this, what's the one big idea you should walk away with? It's this. The whole challenge, the entire quest to build a clean, perfect amplifier really just boils down to one thing: creating and maintaining a stable Q point. It's not just about picking the parts, it's about designing a circuit that can hold that perfect idle setting no matter what. Stability is, well, it's everything. And that leaves us with one final exciting thought. Now that we understand how to build this fundamental building block, a reliable single-stage amplifier, what's next? What kind of incredible, complex systems can we start dreaming up and building with total confidence?